Okay, so I hope that y'all watched the video on vibrational partition function. And so that kind of finished out all of the pieces. We had translation, rotation, vibration, and electronic. And today we're going to see how these partition functions can feed into the energy of the molecule or atom. And then we're going to use that energy to determine all the other thermodynamic properties. So we can determine the entropy, the enthalpy, the Gibbs energy. There's a Helmholtz energy too, and the equilibrium constant eventually. So it's a pretty exciting progression here on today and then the next week. So what we're going to do today though is I want to go fairly quickly. I'm sad we started a bit. I mean, we had to handle some business, so that kind of put us behind. But I'm going to go through this one fairly quickly. There's a longer lecture on the same material, so if you want to go back over it, you can do the longer lecture, because I want to get to the spreadsheet version of all of this. So we're going to take all of our equations that we learned from the molecular partition function and put them into action. But let's start with this bit on the statistical thermodynamics. So this is how we take the two-level system and turn it into energy and enthalpy and all of those things. So this is, again, the statistical part of thermodynamics. It takes the energy levels, which we're throwing molecules at, kind of like we roll a dice, and then we're turning that into the thermodynamic functions. So we're connecting quantum theory to bulk properties, and we have these different parameters. So we have the heat capacity, a constant volume, a constant pressure. We're going to learn a lot about that today. And then we're going to learn about energy, entropy, enthalpy, Helmholtz free energy, and Gibbs free energy. And y'all have heard of the Gibbs free energy, I know, and the equilibrium constant. And you've heard of enthalpy and entropy. Okay, Helmholtz may be new for you. So this lecture is just going to focus on heat capacities and on the energy. So you have a decision point. Whenever you're asked to calculate the internal energy of something, you need to decide whether you can count the number of levels or not. Okay. And so if you can count the number of levels, like a 2-level or even a 5-level system, there's no difference calculation-wise between a 2-level and a 5-level system, except it's more tedious to do the 5 levels. You're calculating the Boltzmann factor 5 times, adding them all up to make Q and all of that. Okay, so if you have a countable number of levels, then this is what you would use. Now this piece right here, this piece right here is the probability of being in state I. So all we have in terms of our calculation of energy is what's called the expectation value. You take the probability of being in each energy level times the value function. Remember when we did the dart game? We had the probabilities of the red and the green and the blue circles, and we just multiplied those by the dollars. Well, we're not interested in dollars, we're interested in energy. Although you can go check your electric bill, they're the same thing. You pay a certain amount for the energy. But we take the probability of being in each energy level and we multiply it by the energy, add all that up, and it gives us the average energy. And we'll do some problems with that in the future, but not today. Now, if you don't have a countable number of energy levels, then we would use the equipartition energy. And we'll get to that in a second. But once you have the internal energy, look how everything else is built on that. Okay, so we start with the internal energy, which is U. And then look at the entropy. The entropy is U over temperature plus the natural log of the partition function. So the partition function is directly related, well, it's logarithmically dependent, but still it's related to the entropy. So when we talk about entropy, you've heard of it being, well, let me see if you've heard of it the way I expect you've heard of it. How would you describe to somebody what entropy is? Yeah, increase in disorder. You hear that. They say, well, okay, entropy is a measurement of the disorder in the system. What is disorder? Disorder is simply statistical options. Yeah. So if I have everybody in here, if I have 22 students and every seat is filled, that's a very orderly system, right? And it's only one way to put this classroom together. I've got one butt in every seat. And that's not disorder. That's a very low entropy system. If I have you guys here now, this is a very high entropy system because you have lots of options and seats that you can pick. Okay, and so the The entropy is related to the partition function, and we can see that. Now, once we have the entropy and the internal energy, look at else. We can calculate the enthalpy, the heat of the reaction. So enthalpy is internal energy plus RT. This Helmholtz energy is internal energy minus T times S, and the Gibbs energy is the enthalpy minus T times S. So we have all of those thermodynamic properties if we know the partition function and the internal energy. And you'll see this. You'll see me abbreviate this as USHAG because it's all of them: USHAG and K. So when you hear about the USHAG problem, I'll talk about it on the exam. You're going to have a USHAG problem. That's what I'm talking about. You calculate all of these things. Okay. So now, if you have a equipartition of energy, meaning you have a high enough energy that there's a sort of an uncountable number of energy levels. I mean, we can calculate it, but it's not like we're counting in a sum. We're doing an integral. Okay, then we would use the equipartition energy. So when the volume is much greater than the thermal wavelength, or when the temperature is greater than 10 times the rotational temperature, or when the temperature is 10 times the vibrational temperature, then we have these, the internal energy is just these values. Notice it's a totally different equation. We're not calculating probabilities. We're not using Boltzmann factors. We just need to know the temperature and the ideal gas law and the number of moles. And then we have 3 degrees of freedom for translation. So we have 3 halves of those. If we have rotation, if it's a nonlinear molecule, we have 3 rotations, so it's 3 halves. If it's linear, okay, it's only 2 halves because we only have 2 rotations in a linear molecule. And then for translation, it's 2 halves for vibration. I'm sorry. For vibration, it's 2 halves, which is just 1. So it's nRT for vibration. Okay. So that's the internal energy. And so we'll talk about this today. This is a very important point, though. Notice this criterion is very hard to meet. So the temperature is got to be around 10 times the vibrational temperature for it to contribute to the internal energy. And vibrational modes are, some are active at room temperature. Like if you got a big molecule, like as big as me, this bending mode is a really low frequency mode. Okay. And so low frequency means it might be 10 wave numbers. If you multiply or divide by 0.695, you convert it to temperature. So maybe it's 13 Kelvin. Well, gosh, that's going to be, active at room temperature. 13 Kelvin here, room temperature is 298. We're way above 10 times the thermal temperature or the vibrational temperature for this mode. But for the CH stretch, that's 3,000 wave numbers. And so we would have to be, at, 40,000 Kelvin, 10 times 4,000, to activate the CH stretch. We're never going to activate the CH stretch. Molecule would fall apart. So this is the decision point. If you use these formulas, if you're dealing with moles of particles, or you see the word equipartition in the problem, or you just, are dealing with, even translational motion or rotational motion. So those are just some pro tips. Okay, so let's, electronic, we don't even put in there because we talked about that in the last lecture, that the electronic excitation of the electrons is just too high, too far apart for thermal energy to populate them. Okay, so these lights here, we do have electronic, we could say these lights are consistent with an electronic temperature of like 6,500 Kelvin. Well, that glass would melt if the gas inside that tube was 6,500 Kelvin. So why does it not melt? Well, because it's not at equilibrium. We're talking about thermal equilibrium, okay? The electrons between the 2 electrodes in those fluorescent lights are flying through. They've ionized the mercury. Mercury is giving off its light as electrons fall back down into its electron cloud, and that's what we're getting is atomic emission from mercury out of these fluorescent tube lights. And the light coming out of that, if we compared it to a black body radiator, would be equivalent to 6,500 Kelvin. but it's not at 6,500 Kelvin. It's equivalent to that. That's how much light is coming out of that. If it were a black body, if we heated up an object to 6,500 Kelvin, it'd be bright white like that. So that's what we mean by electronic temperature. Okay, but the translational temperature and the rotational temperature, if we hold onto that tube, it's warm, so it's a little bit above room temperature, but it's nowhere near the 500 degrees you would need to melt Pyrex. So, and that's a good thing, because anything that touched it would start smoking and everything like that. Like those quartz halogen lamps, you ever had those as a kid? A moth would come and hit that lamp because it's attracted to light and land, and then it would start smoking and stinking because those lamps burned really hot and they were fire hazards. So they kind of got rid of them. People would, they would catch fire. Okay. So these are the heat capacities. Let's talk about heat capacity. So that's a really important term. It is the change in internal energy with respect to temperature. So this is the thermodynamic definition of heat capacity. And so if it's the derivative of internal energy with respect to temperature, this has got to be the easiest derivative you'll ever do. Okay, so du dt, and this is u. So 3/2 nRT. There's a big old T to the first power. Okay, take the derivative with respect to t. T goes to the 0th power. Okay, and you pull out the coefficient. And so this is the derivative with respect to temperature of the internal energy for translation. 3/2 nR. And R is the the gas constant. Okay. And the rotation, same thing. Only this for a linear molecule is the derivative of 2/2 nRT, so it's 2/2 nR. I'm leaving the halves on there because we're going to add them all up, and we have these units of nR. And then the nonlinear would be 3/2 nR. And then for every vibration, I've added an A in here. That's just the number of active modes. Okay, so it's equal to nR, but we're going to put an A in there as the number of active modes, because in a bigger molecule, some modes will be active and some modes won't be active. Okay. So when the temperature is 10 times the vibrational temperature, that mode becomes active. Okay, and then the total is just the sum of all of these. Okay, so here it is, this total heat capacity, constant volume, in terms of per mole. Then this is per mole. It's 3/2 nR plus 3/2. So if we divide by per mole, if we bring the mole over here, then we have this 3/2 plus 3/2 plus A times R. And you need to have R memorized. 8.314 joules per mole Kelvin. Okay. So what does this tell us? Well, this tells us we could store, you've got 3/2 plus 3/2. It's essentially 3 plus A times R. So what is the heat capacity? Well, this is the amount of energy, 8.314 joules per mole of energy put into the system to raise it 1 degree Kelvin. So every degree Kelvin requires that much energy. Now, why is that a heat capacity? Because this is different for every substance, okay, based on the number of vibrational modes that they have. Okay, and so we can in a given bucket of temperature change, let's say things go 10 degrees, substance A can hold 50 joules and substance B can only hold 25 joules. And what is energy? Energy is the capacity to do work. So if we have a higher heat capacity, we have more capacity to do work in that substance. So that's why we're interested in this. Okay. The number of active vibrations. So like if I have a molecule has 3n-6 vibrations. Remember that. So there's a bunch of them, and only some of them will contribute to the heat capacity at your temperature. So if we're at room temperature, only the really low vibrational frequencies will contribute to the heat capacity. It would give you a wrong result to calculate for water those 3 vibrations that water has. the bending mode is 1500 wave numbers. It's not active. And the CH stretch, asymmetric or symmetric, are in the 3000s, not active. So for water, A is 0. So water's only going to have 3 times R. So 3 times 8, that's what, 24? So water's heat capacity is around 24 joules per mole Kelvin. Okay. Now, if we just have a monatomic gas like argon, it only has translation, so it doesn't even have rotation. So it's 3/2 times R, so it's 24 divided by 2, because 24 was 3 times 8, 3/2. Divide that by 2, you're down to 12. So argon only has 12 joules per mole per Kelvin as its heat capacity. So think about that. I can store twice as much energy in water at room temperature than I can in argon. So water at room temperature has twice the ability to do work for me than argon does. And this is a really important thing when we get to engines, because we're going to stuff energy into gas in a piston and have it push that piston. That's work. All right. And I want something in there. Heat capacity is really important. I stuff something in that piston. I want it to have a lot of heat capacity so it can push that piston. I have more capacity to do work in a given temperature change. So that's the important thing that we're leading towards. This is just saying that if you try to get into the electronic energy levels, then you're going to break apart the molecule, because you're going to start populating those antibonding orbitals. So here's some heat capacity data from the CRC. So here we have, again, these monatomic gases. We just did this, right? We did 3/2. So 3 times 8 was 24, divided by 2 is 12. And here we have argon, copper, and mercury, and they're the same. Because their electronic energy differences, the electronic cloud doesn't matter in thermal processes like this. Okay. So anyway, this is, gaseous argon, a gaseous copper atom, a gaseous mercury atom. Those are all 12.486, 3/2 R in terms of their heat capacity. It's weird. I don't know why aluminum is 13, but let's go on over here to this. So 3/2 R is so this is the sort of the what I want to say, the theoretical or theory. Okay, and here's the difference, right? Here's experimental and theory. So the difference is the experimental is a little bit higher than the theory. So not sure where the difference is theoretically, okay, but anyway, something going on there. Here for bromine, carbon dioxide, carbon disulfide, what's unique about these 3 molecules? Linear, so now we have rotations. So now we have the 2/2 R added in. You see that? So 3/2 plus 2/2, we have 5/2. So 5 times 8 is 40 divided by 2, 20. So here we are at 20. So this is the theoretical. And then here's nonlinear molecules like water, ammonia. So we have the 3/2 R, and we're at the 24 or 25. Okay, calculation. So here, I'm not sure what's going on with the aluminum and uranium. Here's bromine, carbon dioxide, and carbon disulfide. And then here's water, ammonia, and all these others. Okay. So look at the differences. So this one, I just have a big question here. Maybe uranium is so big that those far out electrons are excited a little bit, and we're storing a little bit of energy in the electronic cloud of uranium. It's absolutely enormous with 92 electrons. Okay. Here, bromine, it's 6 point, the difference is 6.9. That corresponds to about 0.8 of an active vibration. Okay, so that first vibration is like 83% active. All right, carbon dioxide and carbon disulfide. Here, carbon dioxide, the bending mode is starting to become active a little bit, 24%. Okay, active, and then about half the vibrations in carbon disulfide are active. So that's interesting. Here, water, only 1% can be attributed to the vibrations. Okay, the rest is straight up translation and rotation. So we don't even have to worry about the vibrations in water, and really not even ammonia. We're only one joule per mole off in terms of its heat capacity. But look down here at carbon C60, right? The theoretical value is 24.9. The experimental value is 503. Okay, so we have about 56 vibrations that might add up to that. So there's a maximum number of 174 vibrations, and so we're activating about 33% of those vibrations in C60. So the only thing that you need to know from this is the base assumption is these right here, right? Calculating these, like for a nonlinear molecule, it's 3/2 R for translation, 3/2 R for rotation, and you get this theoretical value, okay? And then if I tell you that 1 or 2 or 33% of the vibrational modes are active, then you need to be able to figure that out. You'll add in like a 33% of R, and you have 33% of this 174, so you multiply that by 30.33 and you get 57.6, and you take that times R, and you'll get really close to the experimental value. So this is the full calculation as calculated by Gaussian. It does the 3/2 R assumption on translation, the 3/2 R assumption on rotation, and then it explicitly calculates the vibrational contribution to the heat capacity. And so these are the numbers that come out of Gaussian. So here's the calculation for C60 that I just talked about. There's the translation piece, there's the rotation piece, and then the vibration piece. If 33% of its vibrations are active, okay, you have 3n minus 6. This is C60, so n is 60. Okay? So it's 0.33 times 174, and it gives us 58 vibrations that are active. And so that's A, 58 times 8.3, we get 482. So we add those together, and we end up with this 507, and the literature value is 503. So we're pretty close. So you can calculate experimental values for heat capacity, but you've got to know how many vibrations are active. That's the difference between all the materials that you see in terms of how they absorb and collect heat, is their vibrational motion.
So the equal partition, the theory one, it counts A as 0 for
Yeah, so just don't incorporate vibrations at room temperature. Like if I say calculate the room temperature heat capacity for a substance, even though it has 3n minus 6 vibrations, I'm going to be giving you small molecules. So ammonia, water, those kinds of things. None of those vibrations are active. So you don't even take into account the vibrational contribution to the heat capacity. Now, there'll be a clue if I want you to. I'll say now calculate the maximum if all vibrations are active. And so then you calculate 3n minus 6, that's A, all of them are active. And that'll tell me you know what you're doing. Yeah. Okay. We do one more, but I'm going to go quick. This is argon. Argon, don't be tricked, okay? There's no rotation. It's an atomic gas. There's no vibration. It's an atomic gas. So all we have is the 12.47. So there are 10 moles, though. So you got to take into the 10 moles into account. And so this would be 10 moles times the 12.4 joules per mole Kelvin. So you get rid of the per mole, and you end up with 124 joules per Kelvin. And so the literature is 124.8. We calculate 124.7. That's pretty darn good. Okay. So let me jump over to the spreadsheet, and I'm gonna stop the video and start it again.